Hey Chris, what you doing?
I was playing guitar.
Those are some nice string oscillations. Is that the sound waves?
They might be. I don't know. Let's find out. Sound waves are mechanical waves. Sound waves, unlike light waves, cannot travel in vacuums. Created by the air, sound waves send energy longitudinally through a wave and to other objects. Due to this longitudinal motion of the particles of air, regions of air are compressed together while others are spread apart. These are called compressions and rarefactions, respectively. When there's high air pressure, it's called a compression, while low air pressure is called a rarefaction. Wavelength is measured from one compression or rarefaction to another. If you were to look at a wave moving to the right, when the string moves to the motion of the wave, it creates a compression. When it moves the opposite way, it creates a rarefaction. This always travels at the speed of sound, which is 343 meters per second. Frequency is measured by the number of oscillations per unit of time. Frequency is the same as its pitch and is measured in hertz. A single note on an instrument emits a single pitch.
To demonstrate how guitar strings compress and rarefy air particles next to it, we will show the difference between an acoustic guitar with a large sound box and an electric guitar without one. By plucking a string, vibrational motion is caused. This vibration will in turn vibrate the air particles surrounding the string into the same natural frequency. With a sound box, the strings vibrate the air particles within, which will in turn cause the whole body of the guitar to vibrate. This will naturally amplify the natural frequency because there is a much larger surface area vibrating the surrounding air particles. Without a sound box, the only sound emitted is from the string's surface area, which is not much at all.
When two sounds have a difference in frequency that is more than 7 Hz, there's interference and superposition of the two sound waves, like this. When two sounds have the same frequency, there's no interference, like this. Interference is a combination of two or more waves that causes superposition. So when the height of one wave is added to the height of another wave. Constructive interference is where the amplitude is equal to the sum of the amplitude of the individual pulses, like that. But destructive interference is when a negative and positive pulse combine and cancel each other.
Natural frequency is the frequency an object gives off without any other disturbance. But can we break this wine glass by vibrating it so intensely by using its natural frequency? First, we have to talk about resonance. Resonance occurs when one object's vibration at a certain natural frequency causes another object with the same natural frequency to vibrate as well. For example, you could hit a tuning fork with an object to make it vibrate. Then, you hold the tuning fork next to another tuning fork that has the same natural frequency. The second tuning fork will begin to vibrate due to the vibrating air around it. It will not need the vibration of the first tuning fork for it to continue vibrating.
So what we're going to do is we're going to show you that a wine glass will vibrate based on using the straw, using the natural frequency, which we have determined is 842 Hertz based on that tone. So we're going to play that tone using my computer through the speaker here, and we'll show you the vibration. The first thing we're going to do is we're going to play a tone at around 800 Hertz to show you that there is a tone going, but the straw on top is not going to be vibrating. And then we'll show you a tone at 842 Hertz, which is the natural frequency, and show you how it vibrates at that point.
So Chris, are the vibrations that I see sound waves?
No, actually, the vibrations you see on these strings are just the strings vibrating, but they're vibrating the air around it. So the vibrations that you see in the video aren't actually the sound waves, but they're causing it.
I'm driving 85 in the kind of morning that lasts all afternoon. I'm just stuck inside the gloom.